Well, thanks very much. It's really an honor to speak here. A lot of people I've respected for a number of years here. What I'm going to talk about is the application of, you can look at it one way, is the application of technologies from microelectronics, or we like to call it nanomanufacturing technology. And I'll give you a definition of what that is to clean energy. So first, for those of you who don't know Applied Materials, founded in 1967 in Mountain View. We're known through most people know us as the #1 maker of equipment for semiconductors, the equipment that manufactures computer chips. But more recently, we've branched out into other areas, and actually last year became the #1 maker of equipment for photovoltaics. We spend and continue to spend on the order of $1 billion a year in R&D. So one of the problems our company has is people invest in factories and then stop and invest and stop, and yet we've constantly invested over $1 billion in R&D. We're also very global. More than 80% of our revenue is outside the United States. And so, for instance, in this one, flat panel displays, 100% of it's outside the United States. There's no one who makes the flat panels of a flat panel TV today in the United States. So where does this start? It starts with nanotechnology. And many people credit kind of the thoughts of this back to Feynman in '59 about what you can do on a small scale. Kind of the first person to really forecast this in electronics was Jack Morton, who talked about doing things at a very small level. And in fact, there's many examples in microelectronics today where we take advantage of small size. It's not just making a feature small. There are physics that go on in these small devices. I just showed one example here of strained silicon where you use a very small device with selective epitaxy to adjust the lattice spacing and get more drive out of a transistor. That's something that only happens at this small scale. So it starts with nanotechnology. That's really the basis of what we do. But we like to call what we do nanomanufacturing technology. What's the difference? Well, just a little cartoon. Many of you that work in a research lab, this might look familiar. Somebody doing something under a microscope or whatever. That's nanotechnology for sure. This is not nanomanufacturing technology. It's not finding 1,000 or 100,000 people to do this. You've got to find a way to do this in a machine where you only have a couple people running it. It's running continuous output. It's repeatable. It's robust. It's controllable. But one of the points I'm going to try and make is one of the most important aspects of it is cost effectiveness. It's got to be cheap. And it may not sound like science, but it actually is. And I hope to demonstrate that to you, especially in some of these energy areas, that cost is critical. So I want to start with the background of microelectronics, and many of you may know this. Moore's law and scaling, where we made the transistor smaller and smaller, so you ended up with more and more transistors or memory bits on a chip. That's the basis of Moore's law. Many good things happened because of Moore's law, and in fact, the industry forgot why Moore originally proposed Moore's law, because so many things got better. You got more chips on a transistor, you got smaller systems, speed increased, the clock speed of a microprocessor, power actually reduced. That was an interesting one. If you hadn't gotten new technology, we never would have been able to run a cell phone on a battery because the operations would have been too energy intensive at larger dimensions of transistors. All of those things got better, so everyone just said, just Moore's law, just scale, everything gets better. It turns out, though, that there was probably one that was maybe more important than others, and it certainly has gotten more important in some of these other areas, and that's cost. So another way to look at Moore's law is, as we scaled, what happened to the cost of a transistor? And when Moore projected this, he talked about reduced cost as being really the primary reason for his law. And we've seen that, transistors going from $1 a transistor in 1968 down to now almost nanodollars per transistor. So just to put that in perspective, I like to use this example. The iPod today, 4 gigabyte iPod, well, maybe it's a couple years old now, $200. That would have cost $1 billion in 1976. Of course, it would have taken about the size of this room and a few car batteries, rooms full of car batteries. But cost is critical. This product never would have taken off if it had cost even $10,000. So taking advantage of these costs and points at which enabled the PC, enabled the cell phone, a good part of it was cost. So given that, and take it on faith here that when we look at other markets, this is going to be as important, if not more important, we want to look at cost. So making something, how much does it cost to make something per function? So in integrated circuits, it's per transistor or per bit. In solar, it's going to be per watt. How do we look at that from the point of view of nanomanufacturing? Well, we can split it into two pieces, a numerator and a denominator. The numerator is the process cost. You're going to make a wafer or a flat panel display. How much does it cost to put down the material or manipulate the material per unit area? So that's a numerator. That's what Applied Materials does. We try and make this as productive as possible. The second part is how much functionality do you get per unit area? So how many transistors do you get per unit area? How many watts do you get per unit area? Now, it turns out for semiconductors, Moore's law was all about this. What he said was, we're going to put more and more transistors on a chip. You raise this, you lower the cost, as long as you don't blow this up. So one of the challenges is as technology gets more and more sophisticated, to make sure we don't allow this to overwhelm this, that it costs so much to do the process to make more transistors that you don't get cost reduction. And I'll give you an example. People have known and used for many, many years electron beam lithography to make very, very small lines. But to try and make a chip with it, you just get ridiculous costs. It never was worthwhile to do that. You'd never reach a lower cost per transistor. So a lot of technology was developed with that in mind. And a big part of this is making tools that do the same thing or do even more fine geometries and layers, but do it faster and with less material cost to drive this down while this is going up. So here's an example, a more recent example. This is so-called high-K metal gate. So through the year 2000 and the early part of this decade, CMOS transistors were very simple. You just had a substrate, you grow it, same oxide for the N-type and the P-type, you put a polysilicon layer, you cut it, and you might dope each one, and that was it. It was a very simple process, same materials on each side. Now we're going to have different materials in the oxide. We have hafnium oxide, we have silicon dioxide, we might have a nitrided oxide. We have metal gates, we have polysilicon and different metals for the NMOS and the PMOS. All of this is adding steps, and if we're not careful, so instead of one furnace tube to do this whole thing, we now have 3 different systems with multiple chambers. So you better get a big impact, and you better have these tools very high throughput and low material cost. Otherwise, this is going to blow up, and you're not going to get the cost reduction. So that's what silicon has been about and continues to be about. Now, let's look at some other areas. This one is one that's happened more recently than integrated circuits. It seems like it's ubiquitous today, but if you go back 15 years, most people had CRT monitors, and really we were just entering the laptop phase. And the laptop, for flat panel displays, an LCD display enabled it. You couldn't carry around a CRT with you in a laptop. As the cost came down, that led to monitors being cost effective, and monitors use less space. And then you came to the flat panel TV. That's happened over almost 20 years. That industry is over $100 billion. How did that happen? It came through cost reduction. And it came through reducing the cost per area of making these displays. There is no transistor. There's no watt per unit area. It's all just about display area. And so we're reducing the cost per watt. And that's come down well over a factor of 10, maybe a factor of 20 or 30 over a 15-year time frame. So approximately you get a 20% bigger TV every year for the same price. And that's been happening now for a number of years. How did that happen? Well, first, what's behind that? This is the typical LCD TV manufacturing process. You make this structure, which is a transistor to turn on and off the red, green, blue pixels in every location. You make a color filter, which has the red, green, blue color that this turns on and off through the liquid crystal. And then you have the thing that basically assembles the whole thing. So there are many steps with thin film layers, with patterning, with lithography and patterning of color filters, and an ITO or transparent conducting oxide to turn this on and off without being visible, the interconnect being visible. So a lot of semiconductor-like processes. How did this work? Well, in this case, it's all about, there's nothing here. This isn't relevant. It's all about how much process cost per unit area. And in this case, when that happens, when it's driven principally by process cost per area, we go to large formats. So I don't know if you know, but your TV that you buy today, and actually this is one generation old. This is Gen 8. We're now up to Gen 9 or 10. It's this case, I think this one's 5 square meter substrate cut into multiple TVs. And so that drives down the cost per unit area, drives this down to make this possible. And these are the pieces of equipment. You're going to see more of this, but this is actually a CVD system, and this is a person here. So you'll see some more big machines like this shortly. But all of these processes at their core require nanoscale precision. I'm going to show you more details of that in energy. And in some of the energy applications, and you have to do it across this big substrate. That is a major technical challenge. So this just shows you when Applied entered the flat panel business, the tool looked like this. It wasn't much bigger than a semiconductor tool. In fact, the company thought this was a good idea to get in this market because chips were going to use the same size very shortly. But what they didn't realize was every 2 years, we started scaling up, and this is the latest tool we have now. It's 9 square meter substrates, pretty big. But it's important to realize that you're getting orders of nanometer level uniformity, but it's over a huge, huge area. And we do over 50 of these substrates going in and out of one of these machines. So imagine 50 garage door size substrates going in and out of this machine an hour, all having to have films with this kind of uniformity. That's what this business is about. So let's look now specifically at energy. So where are the opportunities? So we look at conservation or efficiency, generation, and storage. The technology can improve performance. It can improve the form factor. A battery, a car battery, one of the keys is can you get it to fit without taking up a lot of the space or weight? And then always cost. And I hope, again, that you agree with me that cost is going to be essential. In fact, again, probably preeminent in all of these. So let's start with energy conservation. So if you look at, these are kind of old, but I think they're still representative of where does electricity get used in a residence and commercially. It's your air conditioning and heating and your lighting, commercially and residential. Those are the biggest hitters. So it turns out that those are 2 areas we can do something about with technology. So first, an example of what we can do with the air conditioning and heating. This is something that's been developed really made commercial over the last maybe 10, 15 years. It's called low emissivity coated glass. So we take a standard glass and we coat it with a metal oxide set of films, And what we do is basically we try and keep, if you look at this from the outside and this is the inside and it's a hot day, you try and keep the IR heat out and let the visible light in. So you get the benefit of the window, you get the natural light in, but you try and keep the heat out. You might also try and keep the UV out to stop damaging furniture or paintings or what have you, if you really want to get fancy with this kind of technology. And the other way works too, if it's in the winter, to try and keep the heat in. So obvious, why wouldn't this work? Well, it all comes down to cost. Right? If you can make the glass has got to be more expensive. You're going to be coating it. And so is that glass going to give you a payoff? So here's an example. This is with different levels of sophistication of the coating. It shows an average energy bill, a monthly energy bill in Phoenix and San Antonio in a 2,000 square foot house. And you can see you can reduce your energy bill just with this glass. And at some point, you get the return on investment. It's worth paying for that glass. And in fact, many parts of the country now, this is a standard that certain levels of this glass have to be used. And just to show you, a lot of famous buildings have this kind of glass now. In fact, more and more buildings have this kind of glass. I think in 2007, maybe 25% of the world's architectural glass was coated. That's going to go up to over 50%, I think, now or very, very soon. How is that done? It's in a machine like this. About 90 meters long. One panel comes out every 20 seconds. A panel is about 10 square meters. Excuse me. But a key is, again, it's nanometer uniformity. Nanometer uniformity across a panel this big. Otherwise, you would see it. You could see it in the streaking of the glass if your eye can see that, unless you have that kind of uniformity. But to make it cheap, you have to do this kind of level of productivity. So that's the challenge. Now, there's more advanced forms. This is kind of a passive glass. This one is one kind. I'll show you another kind soon of an active glass. This one's known as electrochromic. So if you look at this graph, here we have the amount of heat that comes through the window versus the amount of light. You'd love to be down here, lots of light through and no heat. These passive glass are here, low E, triple low E. This glass you can electrically tint. So it's like a battery. You can move ions through it and color it. And in that way, you can dynamically move up and down this line. So if you have very bright sunlight, you can detect it and then flip the material, and vice versa. It's a tricky technology. It has lifetime issues. It has matching issues. It has, but maybe more than everything else, it's got cost issues. So this is a very sophisticated stack over 10 metal or dielectric layers. Again, most of them less than 100 nanometers thick. To do this, we have to get the cost down to make this technology adaptable. It's got to be at least the price of low E glass plus a mechanical shade for this to be widely adopted. But it has potentially superior benefits to just a passive glass. Of course, I don't need to go through this here. A lot of the leading edge work in solid state lighting is done here at UC Santa Barbara, but this is the other one, lighting, key area to target. Why? Because solid state high brightness LEDs can drive the amount of light per watt that you get out. So as that goes up, you're using less electricity to get the same amount of light. Also, the lifetime goes up versus, say, an incandescent bulb or even a compact fluorescent bulb. But the problem is, and if you get a very good LED bulb, these are very expensive. And so the question is, how can we reduce the cost of these LEDs and still, keep their energy efficiency going up? So here we're looking at the dollars per lumen, the dollars per amount of light that's being emitted. And we can go after that in the numerator, again, manufacturing cost, and in the denominator, through different factors that add up to or multiply out to the lumens per square meter. I won't go through this in detail, but again, these nano-manufacturing technologies, the manufacturing technology after this, some of the sophistication in the device structure, and quantum wells and so forth going after the denominator. We're pursuing two approaches. We think these are mutually complementary. One is the high brightness LED, here used for point sources, replacement of bulbs or backlights. The focus here is on the conversion efficiency, run-to-run uniformity, and the cost of materials and the total cost of ownership. The other approach that we're pursuing is organic LEDs. These have the advantage that instead of being little point sources, they're panels. And the ultimate application for those, we don't have them in here, but so the luminaire with the 3 fluorescent bulbs, instead of having that complicated structure with the 3 bulbs, you just have a tile. And you just have 2 wires with the tile, no mechanical structure with it. And the focus there, again, is on efficiency, but also on the lifetime. Some of these, especially the blue, has a short lifetime, and then again, the cost of consumables and ownership. In this case, because it's tiles, we're going after these big systems. In this case, it's more like a semiconductor process, but we got to improve a number of these factors. Applied is working on a product like this. I can't tell you about it yet until we release the product, but I did want to show this because a number of people think Applied is only a silicon company. Also that history kind of repeats itself. So this was an advertisement from Applied in 1971, and if anyone here makes LEDs or even does it in production, this will sound very familiar. With this new reactor, you can produce run after run of LEDs to the tightest specs without tearing down the system between runs. Most MOCVD reactors in production today require you to lift the thing up, take a rag, and wipe it down, and use a glove box to put the wafers on it. I'm not kidding. That's still the way it's done today. And that's not going to work if we want to get this into really volume applications and replace light bulbs and such. So we're working on that. Look forward to, in fact, engaging some of the folks here when we develop a product in this area. In the meantime, we have developed an OLED product, and actually you can buy light tiles from Philips made with this tool today. What's interesting about the LED market goes to this whole issue of the learning curve. So this was the market, the current market, or up until this year, the market for LEDs. We call it specialty. It's your cell phone, it's braking lights, traffic lights, areas where you need either the brightness, the lifetime, or the power. So in a cell phone, you'll pay for the LED because it uses less battery, and that's really worth it. It's not that much more money, and it's really worth it. The next big market is happening right now. It is not the replacement of the light bulb. The next big market for LEDs is the backlight of LCD TVs. And in fact, Samsung really has championed this. So the hottest selling TV today is one that replaces the fluorescent backlight to light the liquid crystal and through the color filter with LEDs. It's thin, it has no mercury, which fluorescent bulbs do, and it uses less power. So that now is driving huge volumes in this industry, which will then lead us to this being adopted for general illumination, really driving the scale. So right now, this is the focus. Although this is ever more being adopted, this is really what's going to drive the cost. And if you think back to the waves of flat panel displays, there was laptops, then there were monitors, then there were TVs. This is the same thing. Specialty black lighting, general illumination. That's how we're going to drive down that cost. So I want to spend most of the time on energy generation and specifically solar. That's where our biggest opportunity is. Again, improving performance, form, and cost. So I want to start with, haven't we heard this story before? So some of us have been around long enough. I was a student in this time when Jimmy Carter said wanted to set the goal of 20% solar by the year 2000. In fact, he even put solar thermal panels on the White House roof. It turned out not that much longer, those panels were gone and things changed. Now this wasn't actually, obviously there's some amount of it was politics, and Reagan didn't like the DOE, but in reality it was economics, it wasn't politics. And here's the economics. In the year 1980 and $2,000, year $2,000, the cost of generating a kilowatt hour of electricity, which if you look on your PG&E or Southern California Edison bill, I think average through the year is maybe 15 cents, peak is over 30 cents. In 1980, solar electricity cost $1 a kilowatt hour versus retail electricity 10 cents, 5 cents. There's no government policy that could bridge that gap. It was too big a gap for economics to make the economics work. And so that was the challenge, at least in the U.S. Now, as time went by, a country like Japan, that doesn't have an abundance of natural resources, their cost of retail electricity is higher and solar price will come down. You would imagine they might adopt it first. And we have policies like Germany and so forth. But in 1980, it was no surprise. And then in addition, there was no view of the impact of carbon, which is another potential reason to move and could be an added cost that you can add to some of these, this yellow one, for instance, the coal-generated electricity. But what's happened since then? In fact, I got Bill Yerkes here, who was involved in this factory right here, the first 1 megawatt solar factory in the world in 1980. Its cost was that equivalent to $1 a kilowatt hour. But since then, and I'll show you what was the major reasons for this, this has come down about a factor of 10. There was a little blip. By the way, this is all crystalline silicon photovoltaics. This is based on wafers. There was a little blip here. This is due to supply and demand, and in particular aligned with a shortage of polysilicon that occurred. The price has come rapidly down over the past year, so we're now below this learning curve. Probably too low right now. This is basically for every doubling of output, the cost of solar has gone down 20%. It's a little bit slower than semiconductors and memory, but it's come down. So now you can ask, well, where are we today? And I'll show you shortly. Also, another technology has been, it's always been around, but has really started to find favor, this thin film technology. This is where you deposit, much like the flat panel display or the OLED lighting, you deposit the material on a piece of glass instead of using a wafer. And that has the advantage it's cheaper to produce. And I'll show you shortly, it has other benefits, potential benefits as well. The way we look at these, this technology is the most versatile, can be used for the most applications. It's especially good on rooftops, especially good on home rooftops. This technology is especially well suited to large solar farms on big pieces of land. And again, I'll show you why that is shortly. But just like these other areas, cost is king. You know, this gets translated into a cost per kilowatt hour. I'll show you how that happens shortly. But for now, let's just look at the production cost per watt of making these panels. You can split it into two pieces, the process cost again per area, and then the efficiency, the amount of watts you get per panel. The first thing I want to say, and I'll show you on the next slide, that it actually, data bears me out. Research has focused over the past few years in the United States anyway, mostly on efficiency. And that's good. There's nothing wrong with focusing on efficiency. It has multiple benefits. But it's obvious when you look at this equation that if you're really interested in cost, efficiency has some theoretical limits. And so improving it dramatically is not so easy. Improving this, there's no end to what we might be able to do on cost. So when you look at these, this has a huge, huge leverage. There's lots of things we can do that can drive this down by orders of magnitude, whereas this, you know, a factor of 20% would be fantastic. Going to something like, you know, from a sun power cell at 20-some% to 40% typically requires that this go way, way, way up, more than this goes up. So this is really important, and I think it's the same as with everything other than semiconductors. This is at least equal or more important than the denominator. Now, does data bear that out? In fact, yes. So this is a study from the University of Wisconsin looking at 20 years of solar cost reduction. Where did it come from? And it turns out, oops, that one animated, that 43% of it came from, they say plant size, but what that really is equipment productivity, including the size of the factory. 12% was the cost of polysilicon, 3% was the amount of silicon used, wafer size, yield, going to multicrystalline silicon. Only 30% was due to efficiency. So I think that's going to continue to be true going forward. This part is really, really important. We've got to improve this as well, but this is where most of the cost game will probably come from. This is how a solar cell is made. You start with raw silicon, you cast it or pull it into an ingot, you then slice these into wafers, you then make the solar cell on the wafers, you then put them on a panel, wire the panel up, and then go install it. The cost of this process is more than half of it is in these three places, even before you start making the cell. And that's even true with today's polysilicon prices. It was maybe 80% of the cost was this when polysilicon prices were higher. This is how a solar cell works. This is the simplest kind, where you have contacts on the back and the front. You have an anti-reflective coating that sucks in the light, that also passivates the surface so you don't lose a lot of the electricity at the surface. Light comes in, generate electrons and holes. They migrate to either side, and you get voltage and current out of the device. Very simple structure. The key to improving the cost is, one, going to thin wafers. Use less silicon. Two is to lower the process cost to make this. And three is, if you can, raise the efficiency. Raise it in a way without increasing the cost. If you can do all of that, you'll lower the cost per watt. So I want to show you some of the technology that's used today to do that. So the first one is, how do we make these thin wafers? So this is a state-of-the-art wafering machine. What you see here are 4 blocks of silicon, 1, 2, 3, 4, and they're going through, actually 1, 2, 3, 4. They're going to go through a mesh of wires. Those wires are 100 microns or 120 microns thick. They run at kilometers per hour along this web. And we have a slurry, and you just push those ingots through. And the idea here is that with this mesh of wires, and these wires are like what you have in a steel-belted radial tire. You waste as little silicon as you can by using a very thin wire, and you put the wires as close together as you possibly can to make the wafers as thin as possible. And we can make wafers now this way that are 100 microns thick, although in production today, most companies still use about 180 microns. So part of it is making the wafers thin. The other part is making the cost of doing this slicing cheap. And that's why in this machine we're trying to do as much as we can in parallel. 4 ingots and actually double sets of wires. I won't go into the details, but this is to lower the cost to cut these wafers. Once you have these thin wafers, now you want to go and make solar cells out of them. You put them in a line. It's not so simple. Thin wafers, in semiconductors we use wafers that are hundreds of microns thick, and they're single crystal, they're nice and strong. This is what I'll just show you a little video. This is a slowed down camera. This is I think this is a 200 micron thick wafer. The speed is going to be 400 milliseconds, and you'll see why these are a challenge to deal with. One aspect of why these are a challenge. So this thing is going to pick up this wafer. You can see it wobbling like that. So you don't want to break it. When you put it into machines, you don't want to stress it. You don't want anything to destroy these wafers. You've got to get them all through the line with more and more sophisticated processes. So consideration of how do you process thin wafers, how do you handle thin wafers is really, really important. And actually, the way we do it today is we use contactless pickup, kind of Bernoulli chuck, to pick these up without actually touching the wafer. And we can have machines that can do this, 3,000 of those wafers an hour, move them onto trays and off of trays without breaking them. But all of the processes need to accommodate those thin wafers, the lithography process, the the material deposition process, the etching, texturing processes have to work with these very thin wafers. So how about some other things we're doing? So I showed you earlier this cartoon with this one layer of anti-reflective coating, but it actually did two functions. It sucked in the light, an optical function, and the other function was it passivated the surface so we didn't lose electrons and holes. Those are two separate functions that really require two different materials. So one way to do that is to use a stack of materials, the top one to get the light in, the bottom one to get the passivation. And if you do that, you get much better performance. But these have to be tailored, again, for high throughput and highly reliable and controlled films. One of the funny things about this, we introduced a tool. One of the things the customers like about it is color uniformity. So you wouldn't think of that, but that's actually important. People don't like, different checkerboard of blue solar cells. So color uniformity is actually another thing that matters for, and again, your eye can see a very small thickness change in a silicon nitride. Lithography, printing the metal lines. This was a key to really raising the efficiency of solar cells but keeping the cost down. You'll be amused to know that the main way this is done is with screen printing, the same way you do a t-shirt. That's how we kept the cost down. But this is the kind of lines, a little bit better than your t-shirt, 50 micron kind of thick lines. Also, you've got to do it with high throughput, and again, you've got to make it so you don't break very many wafers. Just to give you a feeling for this, one of the hottest things that we have right now is what's called double printing. They have higher efficiency cells, they want to pull out the current, but they don't want to print a wider line, because if you print a wider line, you block the sun from going in, block the photons. So one way to do that is to make a taller line. But unfortunately, with screen printing, you can't just, if you take a screen print, a squeegee, you get the thickness you get. It just depends on the material and the screen. What we do here is put two lines on top of one another. Line 1, and then we put line 2 inside line 1. So we make a thicker line, you get lower resistance, and you don't block the light from coming in. Applied likes it because you got to buy two pieces of equipment for one step. We always like that. But the customer gets the payoff. They get a higher efficiency at relatively low cost. They get their ROI. So this is very hot. And it really shows you, that good technology can lower cost and improve performance. Even if it's a little more complicated, you can see that payback. So where the technology is going are more complicated cells. So not like that one I showed you before, but lots of different materials and interconnects. These are about a year or two old. Both of these are now at about 23% cell efficiency from that basic one that I showed you before, which is probably 15 or 16% silicon cell efficiency. However, to get this, you have to have higher process complexity. It's more steps. So we got to make sure those steps are cheap enough that you get the payback. The other problem you have, and this goes to problems we've had in semiconductors for a long time, is when you have a process that's got lots of steps, the more steps you add, the more variation you add to the process. So if you have only a few steps, you might have a fairly tight distribution, but you add more steps, the distribution of the end product starts spreading out. And if it spreads out too far, you spend all that money to get that more complicated process, to get that higher efficiency, and you wasted it because you got all these low efficiency cells. So as you improve the efficiency, you've also got to improve the factory control and squeeze the distribution up towards the maximum so that you don't get all this wasted low efficiency material. So factory control becomes important. Statistical process control, software to control the tools, to track the cells is important. Let me turn to the thin film solar. So here we're going to start with a piece of glass or maybe a flexible sheet. We're going to deposit all the materials and pattern it right on this piece of glass. We're going to laminate another piece of glass on the top, just like your automotive rear windshield. And then we're going to just go out and install these things in the field. So actually a simpler process. That's why one of the reasons it costs less. I'm going to focus on the glass-based thin films. Simplest structure, You have a piece of glass. You have a transparent conductor. That's a conductor that visible light can go through, and yet it carries electricity. This is the semiconductor that absorbs the light and converts it into electrons and holes, and then you have another electrode on the back. So a very simple process, only a few steps, very thin amount of material. The key is large substrates. The same reason the TVs, we make a big substrate to drive down the process cost and then raise the efficiency. These materials are not perfect single crystal materials, and you have to do some things to make them more efficient. You also don't want to grow a big thick film, so there's some physics and materials that you want to implement there. So this is what we've been working on. This is the size solar panel we can make in this factory, adapting this flat panel display technology. So this one is 5.7 square meters. You can cut it into pieces like this piece. And the idea is you go after this cost. By making it on that big, big, big substrate, you drive down the cost. So this is the tool. That's a CVD system. What this is really for, this is not for your rooftop. So this thing will, there's no way somebody can carry that up on a ladder and put it on the roof, right? This is for, one application is for fields like this, big panels to put into the field. So this is what a factory looks like. This machine here is one of these. There's a little person right here. This is a tandem junction factory. I'll explain what that is in a second. So it has 28 of these chambers to do deposition in these 4 machines. It's got a number of other steps. Rather than point it out on there, I'm going to show you a movie and explain the steps as we go along. So in this case, the glass is going to come in coated with a TCO, transparent conducting oxide. Remember, that's the thing that lets light in but still acts as a conductor. So we pull it from the glass company out of a box with a robot, put it into the line. We clean off the edges, clean off the top and bottom. Now we're going to put it in what's known as a laser scribe that's going to pattern the conductor, the transparent conductor. Comes out of there, goes into the big CVD system to put the silicon on. And there's that big machine again. It's done with a plasma-enhanced chemical vapor deposition, different kinds of silicon. I'll explain that shortly. Comes out. This is a simple model. You then pattern the actual solar cell itself, the silicon. You then put the back metal on, aluminum, some alloys. This is in a modified glass coater, like I showed before. You pattern the metal layers. Now you do what's called shunt busting. You fix some yield problems. You can then cut the panels into multiple sizes at this point because all the expensive processing is done. Fix the edges. Attach a bus line to connect up all the cells. This is a PVB. This is the material that seals the 2 glass layers together, like in your windshield. Put the other layer of glass on, laminate it, heat it up, and make the material flow. And then this is kind of a big pressure cooker to get rid of the rest of the bubbles that might be there. Then it comes out, you put the electrical junction box on the back, and you put it in a machine to measure the efficiency, and out it comes with the stamp on it. That's it. 20 of those substrates an hour out of that machine, out of that factory. Cost is close to $1 a watt today. What's the technology? In this case, we're using thin film silicon technology. There are other materials you can use. We can have an extended discussion about this. Silicon is really the best in terms of doing large substrates. It has some other advantages too. This particular technology is really pioneered in the 90s and really is starting to progress faster, I think, at this point than any of the other thin films. It's known as tandem technology, tandem junction, based on microcrystalline silicon, where you have an amorphous silicon and microcrystalline silicon layers with 2 different band gaps to capture more of the light spectrum, more of the wavelength spectrum of light. We also put in light steering layers that are textured so that you try and get the light that's captured best in each of these layers focused on those layers through diffraction. You also have a mirrored layer on the back that, again, tries to keep it bouncing around in the film that it's best suited for. So you capture as much of the light with as thin a material stack as you can. The trick of all of this comes down to uniformity. We not only have to have in this case, not only do the layers have to be uniform, but the band gap has to be uniform. So the band gap of the microcrystalline silicon has to be the same from one corner of that 5.7 square meter substrate to the other, and we got to have substrates going in there at 20 per hour. That's a real challenge. A lot of things we can do to make this device more efficient. Again, if there are questions, I'll go into comparing this against other technologies. These are some research results showing that you can get 13 to 15% efficient cells with this, so very competitive with any of the other materials that are in production. What are some other advantages, though, that you might not think about? So when you look at the cost of thin film silicon and it's cheaper than crystalline silicon, how cheap does it have to be? Is it just the efficiency penalty that you have to overcome with production cost, or are there other things? And what we found are there other things that help make this more effective. One is the thermal coefficient. If you look at panels that are rated, or a set of panels for the same output in a cool climate under standard conditions, and you actually put them in the field in a desert or in any kind of environment where they heat up when they're actually working, you find that crystalline silicon degrades very fast with temperature. So if you put crystalline silicon in the desert, it's not very efficient. It loses a lot of efficiency. The thin film silicon loses a lot less, and so it behaves better. It gains in performance as it's heated up versus crystalline silicon in a relative way. So that means that thin film panels get higher energy yield in real conditions versus crystalline silicon for equal rated panels. So that's a benefit. A second benefit is the benefit of size. We've found with installers who have installed these panels that you can get a lot of reduction in installation cost for these big solar fields by using big panels. What you do is this one's just a simple truck. It has a glass mounting tool, the same tool that you use to put glass into buildings. They're just suction cups, and you just kind of just put it up onto the building. Here, we're just going to drop it onto this frame. And in fact, you can do it without screws. You can just have the thing fall onto these clips and have it grab the back rail. And in 2 minutes or less, you can install 500 watts. And so you take that truck and you go boom, 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 going down a row. This is the way people install cadmium telluride panels in solar farms, one at a time. The biggest reason is because they can't make them on this scale. There's limitations in terms of uniformity and temperature. And so this lowers the cost. In fact, it lowers it by, we think, 2 to 5 efficiency points. So if you install a panel like this, or let's say this one at 12%, this one, if it's at 10%, it's the equivalent of 13% because of the size. The other thing with size for thin film, which we think is very exciting, and in fact, a number of places around the world are promoting this very heavily. For instance, China, the Ministry of Science and Technology, this is a favored project, is what's called building integrated photovoltaic. So here you thin the layer or you pattern it to make the thin film semi-transparent. Now you have a window that has shading, but also instead of just reflecting that light, takes the light and converts it to electricity, some of it. Some of it comes through, some of it is collected and used for electricity. This is an interesting idea. It's been around a while. You can find some high-profile buildings that have this around the world. You can see some of them here. The problem has been it's really expensive. So you can see you have to use these smaller form factors and laminate them together or use more structure in the window. This can be changed dramatically, again, by using that big substrate. Now you have a big piece of glass. You can cut it into any shape you want. You can cut it. You can use it this size. You can do it this size, whatever size you need. So this allows you to, again, reduce cost, which is a key. There's other things we have to do in terms of laser scribing and other steps to reduce the cost of those. But this application could be very big, and I'll give you the reason why. Shanghai, China. Not a lot of rooftop area, but lots of floors on buildings. So this is an opportunity to have south-facing parts of the building collecting electricity. So how do we convert between, and where does technology take us in terms of cost per kilowatt hour? So I just show you an example here. And the way you do this conversion is there are a few key parameters. One key parameter is how much sunlight you get. So if you're in high sunlight, that's more efficient and you get more electricity out and the overall average cost is less. So if you're in the US Southwest, and let's pick a point here, this is the total cost of installing a solar panel, the price to buy it and the price to install it. So let's just pick this number here, about $3.50. If you're in the US Southwest and you do, this is for a utility installation, the average cost of electricity with the US tax credit that's applied is about 17 cents a kilowatt hour today. If you're in North Carolina, it's maybe 22 cents a kilowatt hour. So it's a little bit higher as you go to low sunlight environments. Another key factor is what's your cost of capital. So solar is very unique because in solar, the only cost is capital. You're going to buy a solar panel, you're going to put it out, it's going to work for 20 or 30 years. There's no fuel. You don't pay for any fuel costs. But you're paying for the capital because you bought it all up front. You bought your electricity for the next 30 years. So interest rate matters. 9% is a typical cost of capital or return on capital that a utility wants. So this is structured for a utility. And what you see is, as we go to more and more improved technologies, we will go down in cost. Now, again, this is for a utility case. What am I showing here? Down here is the so-called generation rate. So if you build a coal plant in Ohio, this will be the cost of electricity out of that coal plant. But coal plants run 24 hours a day. So that's what's known as base load. It's going to be a while before we get to base load parity with solar. And there'll be other issues like storage that you run into. What solar really competes against today is peaking. So during the day, we turn on other sources of electricity because people turn on air conditioners, turn on computers, turn on lights, turn on all kinds of things during the day, washing machines and so forth. That's when electricity costs the most because then you turn on these other sources that you're going to turn on and off and on and off all day. What's the worst time of year and the worst time of day for that? Summer, when the air conditioners are blasting in the middle of the day. Guess what? That's when solar works best. So we compete with solar against peaking, what's known as peaking. Things like natural gas, turbines. So in some places this is diesel. Actually burn diesel to get this peaking because you don't turn a coal plant on and off or a nuclear plant on and off. Right now we are actually competitive with peaking electricity. And so with these incentives. So that's what's really interesting about where we are today. And as it turns out, we're at about the installation costs for the kinds of panels you saw are about $3.50. So we're right in here. If you took all of the solar you could put in that could cover as much of the peaking as you could cover, it's about 30% of the daily peaking because some of the peaking happens in the evening when solar isn't as efficient. That would make about 10% of the electricity used in the U.S. So we could go to 10% before you'd need battery backup and before you'd need to compete with this kind of price. So that's why it's really getting exciting today. And this can make gigawatts literally around the world. Another interesting thing, just to show you the effect of policy, people talk about green banks to stimulate renewable energy. If instead of a 9% return, so say it was you as a homeowner, you went and got a loan and it was 9%, you'd be somewhere up here because you wouldn't be able to use this big installation technique. You'd be somewhere around here. But just take this point. If instead of 9% you had 2% cost of capital, you borrowed the money for 2%, the cost of the solar electricity goes from 17 cents to 9 cents a kilowatt hour. It just shows you the effect. The cost of capital is the cost. If the solar panel lasts 30 years instead of 20 years like this analysis does, it drops the cost. If carbon costs come on in the future, these costs go up. Solar stays where it is. Solar becomes more affordable. If the cost of natural gas goes up over the next 20 years, same thing again. You're locking in your rate when you buy a solar panel. It is what you bought the panel for and what interest you're paying. But the key point here is that in spite of all of this, these are just the incentive, the cost of capital. These are all catalysts. What's going to drive solar is technology driving down the cost. So finally, just a couple points on energy storage. We look at storage. There's a number of different markets, from miniaturized batteries for things like energy harvesting, watches, button battery replacements, smart cards, medical devices, down to backup for solar or wind farms. The ones we think are the most interesting are these two, the miniature batteries and transportation. Transportation, the electric vehicle or the plug-in hybrid, the miniature batteries. So those are the two. I want to just finish with a couple things on that. So one, when you look at an electric system, what's the one piece that really hasn't been reduced yet? It's the battery. This is an area where we can really develop some technology. One example is a smart card. If you have a smart card today, there's no battery and it's passive. If you want to make it really smart and have it flip a code around, you need like these little tokens that a lot of us use. You need a battery in there. But how do you put a battery in a credit card format? So it would be used in a lot of other applications other than that. Everybody wants thin products today. We'd have to do that to get rid of the button battery that are in things like watches, for example. So here, there are various ways. There's material science, but then again, it comes to how do you get this productivity to drive both the cost per area as well as the energy density. And then there's the vehicle market. So the vehicle market, we have two problems today. One is that the energy density is low, so you have to use a lot of batteries in a car, and then also they cost a lot. We need to move to a point where we have something like 3 times the energy density and maybe a factor of 10 less cost to really make the plug-in, next generation plug-in hybrids of hundreds of kilometers range really affordable and usable. And again, we can go back to a lot of different technologies, just highlight a few here, and show you, again, nanotechnologies can play a role. You want to use a process to make 2 electrodes, and then you put the electrolyte between it and you assemble it. Some of the technologies to make more efficient electrodes, to make them 3-dimensional, so there's more surface area. It's a little more complicated than that because they have to accept and release ions and have to be reliable. But surface area is a key, surface area plus reliability. The other is doing it on these different form factors, again, to drive down the cost per area, but to do it on sheets that you can form into shapes that have high packing density. For instance, in a car, and I think in the Chevy Volt, the batteries are these cylindrical shape, and if you pack those together, you miss a lot of area. This is the kind of form factor we'd like to go to, where you can stack these batteries and not lose any area in between them. And again, that implies certain kinds of processing techniques. Finally, I don't want to forget semiconductors. So I started with semiconductors. I want to come back to semiconductors. Chips and ICs have a big role to play in energy. This is an example, the smart grid and smart house. Back to energy efficiency. How many people, if they had a little meter showing how much it costs to turn on their dishwasher at 7 o'clock instead of waiting until 11 o'clock, would push that button, or the dryer, or the whatever, the light, your lighting, whatever it is, or have it done automatically for you, or have it tell you how much the electricity price is on a real-time basis. So a lot of things you can do, and of course all of these systems, whether they're the car, or your thermostat, all will have smarter electronics in it. So I think no one has calculated what the opportunity here is for chips, but it could be the next killer application for semiconductors as well. Every residence, every home, every school, business should be full of this. The payoff would be large. So with that, let me finish. I hope I've justified that this kind of nano manufacturing technology that's been practiced in semiconductors has a wide range of applications. It's more than just making small features, and cost is really a critical element. The cost per function really enables almost every market. I think it's a great time to be a student in these fields in physical science. It's a great opportunity. It's a big challenge we have around the environment, around clean and green energy. But these kinds of technologies can make an impact. We can make a social impact and a business impact and a technical impact. So it's really a great time, I think, to be working in this field and learning and entering the field. And there are a variety of opportunities. It's not just solar, also glass, LEDs, and batteries. All of these will play a big role in solving this problem. And with that, again, I thank you very much. It's really been a pleasure to be here.
That was a superb talk. Thank you very much. Questions? Here? There is a microphone.
One way of driving the cost down, what you showed was still all batch processing, right? And so one way of driving the cost down is if you could go to continuous processing, such as reel-to-reel. What does your crystal ball say there?
So some of it was batch and some of it was inline. So for instance, those glass coaters are inline tools. What we see today, we do, by the way, we do have products for roll-to-roll, so we are involved in that. But what we see today with roll-to-roll is that its principal application is weight. So you don't save a lot with installation. The process cost is actually more. Efficiency is lower. But where it's really done well is some parts of Europe have an extra incentive if you lay your panels flat on the roof. In France, they don't want them sticking up and soiling the view. You put them down, that roll-to-roll technology tends to work really well. It conforms to the rooftop and it has good weight loading. And they give you the extra incentive to make up for the fact that you're not collecting as much energy. The other place, believe it or not, I've talked to installers in California, in the Bay Area, and they told me the #1 application they have for it is schools, because baseballs don't break the flex substrate like they do glass. But I think no one's really, it's not going to, I don't think it's going to be competitive unless there's some breakthrough in efficiency and cost, which we haven't seen yet. There are materials that promise higher efficiency, but they struggle with like SIGs, but they struggle with three things: encapsulation, overall reliability, and heating. SIGs is just as bad as crystalline silicon, essentially, in terms of its thermal characteristics. Having said that, I do think there are going to be markets for these flex things. Our biggest market today, growth market for flex material deposition, is touchscreens, which are showing up everywhere, and I think will even show up on larger, smart boards and things like that, smart LCDs. But right now, the flex solar is still, I would say, a niche application. There's one leading provider, I think, right? It's got maybe 90% of the market's Unisolar in Michigan, and almost no one else is producing very much at all. Any question over here? Yeah. All right, you want to go there first? We'll save you the walk.
Thank you. I was wondering, do you have an idea of what the effect of the cost of electricity itself is on the cost of producing solar panels? So if the price of electricity doubles because of oil or coal doubles, what will that do to the price?
Or likewise, what's the energy return on investment? So I ought to let Bill answer this, actually, because it's changed pretty dramatically since we first started. I think the numbers today are the biggest source of electricity or use of electricity in everything I showed you was actually pulling the ingot, actually forming the ingot. So that's why the leading company in this area is actually renewable energies in Norway, because they sit themselves next to hydro dams, just like our friends at Google. But nonetheless, with the improvements that the crystalline industry has made, the wafering in terms of using less material, I think it's down now to less than 2 years is the payback on electricity. And for thin film, it's less than a year because you just basically use the CVD process. So it's on that kind of order. Is that about right? Okay. There was a question over here.
Although you've spoken about the cost-effective nature of your applied materials photovoltaic modules in terms of cost per watt, does that factor in also the durability, recyclability, and toxicity of materials? Because if toxicity was taken into account for solar's cadmium telluride modules, then it would obviously be much higher.
Yeah. So these are the silicon modules are pretty clean of any materials. There's nothing toxic in those. By the way, again, I will stress, we do sell equipment for CadTel and for SIG. So we think this, from what we know today, without any revolutionary breakthroughs, we believe the silicon is going to be the predominant thin film technology. But we are supplying to those others, and those others may find a breakthrough that changes the game. So I don't want to discount that possibility. But you're right, the cadmium telluride modules especially have some issues about the recyclability. There are some places that don't even want them as well. What's the real risk of these things? How big is it? I think you can argue it may not be as big as it might seem, but it's still not. It's not a great thing to have, and so they have done a good job at recycling this, but that does introduce an additional cost. The silicon ones do not, and in fact, the other thing, I don't know if we know the lifetime of the silicon modules either, for that matter. Silicon. One of the nice things about silicon compared to any of those other materials is it's fairly impervious to water and environmental conditions. You can put a lot more in there and not cause a problem. So those are, they're fairly safe. They're mostly sand, right? So it's a fairly safe material. Yeah.
Thanks for a very nice talk. You've shown very clearly that there have been and there will be likely dramatic decreases in cost for this kind of technology. I'm thinking PV cells in particular. And it always struck me as sort of interestingly ironic then that one of the issues that comes up is when to buy. For instance, I'm the consumer, and the return on investment on my roof system may be 10 or 20 years, leaving aside tax credits and whatnot. Maybe it's a little less now. So if the efficiency is going to be 5% higher and the cost may be half in 2 years than it is today, where do you draw the line? How much do you wait? Would you buy today, or do you wait the extra 2 years?
So, I think first of all, I think what you'll find is probably it'll pay off sooner than any calculation you do, because if you believe that, carbon will have a price or the other alternatives are going to go up. Most of those calculations are done against the static today electricity price. But having said that, yes, I think there is this possibility. It certainly dropped quite a bit recently. However, there is kind of a break on that, in the sense that the technology can go down fairly fast, but that's only half the cost. The other half is installation, and that doesn't go down quite as fast. So even though the panel may be cheaper, unless people are figuring out cheaper ways to install it, which happens can happen at a slower pace, the total cost to you won't go down quite as fast as perhaps the module cost goes down. The other thing is that, I think most places, if it's done intelligently, will, and I think Germany is the key example where they debate this all the time, where they'll move the incentives. Japan as well have moved the incentives as the cost of solar goes down, so that it kind of stays somewhat in balance. Now, Japan went too far, as it turned out, and now, in fact, they just doubled the residential credit in the November 1st again to encourage more solar use, because it is more, they wanted to stimulate it because it is more competitive. So it really depends where you are and what the local environment is, when the credits expire. So, for instance, every year in Germany, right now, there's a big boom in installing solar panels because the feed-in tariff goes down January 1st. So people wait till the end of the year because they know it's cheaper as they wait, but you wait till the end of the year and catch the last bit of that extra incentive before next year it goes down. So the other thing is that affects a residential purchase is, if you think you're going to get value when you sell the home. So if you're going to live there 20 years, then it might make perfect sense. But if you're going to sell the house, then you have to figure out, are you going to get the value back for what you put in? And there's some municipalities that have tried some different things. I think Berkeley, but I think this has been used up. But Berkeley had a credit where they buy it for you and lease it to you. And so that, as another person takes it, that kind of gets passed on in a way that doesn't cost you a capital loss in some way. So I think, what I would say is that, we're at a trough right now if you look at prices. I think prices are going to go back up from where they are now. Now, the retail market may not have caught up with the production cost yet, but it's pretty close to doing that. And once it does that, then it's going to take a little while for it to get back on that curve and come down. And if you combine that with a belief that, if you do believe that the incentives today are higher than they will be, now would be a good time. However, if you believe that Schwarzenegger will get a feed-in tariff in California at 20 cents and not 10 cents, you would be better off waiting because they'll pay for your electricity and it's a better incentive. So it comes down to what you predict about the incentives. If it's status quo, I would say it's probably good to buy in I don't know, maybe, I don't know what some of the benefits in California change again at the end of this year, but it's at a trough where it may stay there a couple of years, the price. Mm-hmm. Mm-hmm. The lifetime of, so I think of, the only risk on lifetime is whether some of these newer players in the field have put all the knowledge base that some of the companies like Sharp and Kyocera that have been in there years and years. So there's some people in the industry that fear that there might be some reliability problems with, for instance, cheap Chinese modules, to overstate it. But other than that, we don't know how long these things last. Thin film silicon's been installed for a long time. Sacramento has a big installation of that. Crystalline silicon. I would say the non-silicon is a risk in that respect. The other issue that a lot of people have is, if you don't have a well-oriented house, it can get expensive and there's a aesthetic issue if you've got to tilt the panels in a particular direction. So that tends to be another impediment. We have a neat one. I'll show you what we did in Applied Materials. Kind of cool. It's hard to see, but this picture is our parking lot. So these are sun power panels. There are cars parking under here. It's about 1 megawatt. It can tilt and track the sun, and we use it for shade. It's a great application. Employees love it. They can the car stays cool, and we create electricity for the campus.
take one more question, and then we'll.
Yes, I often hear argument that solar panel creates less energy than it takes to make it. I mean, what's the energy output per input?
Yeah, that's what I was saying. It takes 2 years or less now. So of the electricity energy you put in, within 2 years you've paid it back. That was a lot longer. I don't know, Bill, what that was when we were doing a lot thicker work. Yeah. Yeah. Again, if you imagine a less efficient way to pull the crystal and having to use thicker wafers, you could see maybe the electricity payback would have been longer, but that's no longer an issue today. It is something that's important to continue to watch across all renewable technologies. Obviously, a lot of them have failed on that basis, so it's a good point.
Well, Mark, thank you for
Thank
very
you.
interesting and stimulating talk.